Okay. So integration by parts. The movie scene from Stand and Deliver that we just watched, this one here, when he did the tic-tac-toe thing at the end, that's they were doing integration by parts by the tabular method. And so we're going to learn how to do that. You're going to see here that Poncho, unfortunately, got off to the wrong start when he tried to integrate this. He assigned the wrong functions to the wrong letters, and that's why he was so frustrated. So he eventually got his confidence back and did very well on the AP exam. Spoiler alert. I wasn't going to say his score. I just was going to say he did very well. Way to go, okay?
Get out.
Anyway, Tito was trying to work this problem here. He was trying to integrate x squared. What's that? Oh, yeah. He was trying to work x squared times sine of x with respect to x. So if I left you to your own devices today with the methods that you know, could you do it? Do we have a method so far that you're just shaking your head no? Why? Because you know it's in this section and there's another way to do it. Well, let's see why we can't do it. It's a product of two variable functions. One of them does not have an inside function whose derivative is the other one. And we're already kind of out of things to do. We can't use a trig identity because sine is already in its purest form. Can't split up anything, inverse trig. U sub is not going to help, so what do? Well, this is going to be a perfect example for what's going to be known as integration by parts. And here's the telltale sign. You have one function that's a polynomial. And if you have like a polynomial factor, that's going to be one of the giveaways. And the other factor is going to be typically either a sine or a cosine or an exponential, but it doesn't have to be. But basically, one of those factors is one that you know how to take the derivative of. You could take the derivative of one of them, you know how to, and you know how to find the integral of the other. Now, in this case, you know how... in this case, you know how to find the derivative and the integral of both x squared and sine of x, okay? So what we're going to do then is assign one of them to the letter u, and the one that we call u, we're going to be taking the derivative of it with respect to u, kind of like when we did u substitution. The other one we're going to be calling dv, and we're going to be finding the antiderivative of it and calling it v after we do that, or finding v. Okay, now in this case, you know how to take the derivative and integral of either one. So if you have the choice, what you're going to want to do is choose your polynomial term to be u. And why? Because what happens when you take the derivative of x squared? It becomes 2x. You make it easier. It makes it simpler. What's the derivative of 2x? 2. What's the derivative of 2? 0. You'll hit 0. If you actually were taking the integral of x squared, bless you, you would get 1/3 x cubed. So you're making it a little bit more complicated. So if you have the option, you're going to assign u, which is the one you're differentiating, to the polynomial term. All right, so let's build up to Tito's problem and the tic-tac-toe method. I'm going to start you off with one that's similar but a little bit easier. X times cosine of x. Can you integrate that before today? No, why not? Same thing, right? It's too hard. We don't have the derivative of one is not the other. Really nothing we can do. So we notice that we have like a power function, a polynomial factor, and a trig function on the other. Sine, cosine, exponential typically are there. Now, one of those factors I know how to take the derivative of, and the other factor I know how to integrate. In this case, I could say that about either one of them, right? I know how to take the derivative and integrate x. I know how to take the derivative and integrate cosine. Which one, then, do you want to call u? Which one do you want to take the derivative of, based on what I already said? X. If you have a power factor, a power function, x to some power, call it u. So here's one way to do it. You could say let u equal x, and that means that dv is going to equal the other factor, cosine of x. If you want to throw the dx in there, that's fine. This is integration by parts. We're going to separate the two factors into two parts. One we're going to differentiate, the other we're going to integrate. Okay, what would be the derivative of u? Well, it would be dx, right? We're taking the derivative in differential form. What would be the antiderivative of dv? That would be v. And what's the antiderivative of cosine? Sine. Plus c. Yeah, we'll throw the plus c on there later. So once you do it like this, if you start with u and du below it and dvv below that, here is how you can get your answer. I call it the backwards Zoro method. Zoro was the guy who went around and you knew he was there. The sound doesn't match like a good foreign film. The mouth. He left his Z all over the place. Well, what does backwards Zoro do? Backwards Zoro, I guess you could call him dyslexic Zoro, but that's kind of pejorative. He does his Z backwards, right? That's how you know he was there. So here's what we're going to do. We're going to do backwards Zoro. This way. Oh, I love technology. We're going to go that way. And then we're going to go down the diagonal, and then across. Okay? We're going to make that backward Z. Now, here's how it works. This first line that we drew actually redefines the problem. If you multiply, you're going to get cosine of dx times x. So you don't have to rewrite that one. The integral then is going to equal the first diagonal, which will be down this diagonal. And what you're going to do is you're going to multiply. You're going to multiply down that diagonal. So you get x times sine of x. So you multiply down that diagonal. When you come back on the last diagonal, it's always going to be minus the integral of. You just kind of have to memorize that. Multiply down this diagonal and then minus the integral of the product of this line, which is going to be sine of x dx. Sine of x dx. So once again, the first pink line that I didn't draw in green, that product redefines your original problem. So that is going to equal the product of the first diagonal minus the integral of the product along the bottom line. So there's still some work left to do, but we have part of it done. So that is, of course, x sine of x. And now we focus on the remaining integral. Do we know what the antiderivative of sine is? It's negative cosine, which turns the minus integral into a positive cosine of x, and then plus c will add at the end, because you're going to have another integral. So product minus the integral of the last product on the line. Now, let's check to see if that's right. Does that look like it's the antiderivative of x cosine of x? See. We'll see. We'll check it. By taking the derivative of that, let's see. The first one is going to require the product rule, isn't it? So the derivative of x is 1 times sine goes along for the ride, plus x times the derivative of sine, which is cosine. Plus the derivative of cosine is negative sine. And then, of course, the c goes to 0. Negative sine, yep, as I said. And the c goes to 0. Now, what happens with your signs in the front and back? There we go. Like a Foley artist, I have to add them afterwards. I get x cosine of x, which is what I started with. So that's called integration by parts. Okay. Pretty cool, huh? Pretty nifty. All right, so backwards Zoro. Why the heck does that work? You're probably wondering that, right? This is going to be annoying here. Okay, there it goes. If you notice, when we took the derivative to check, we did the product rule, right? It comes from the product rule, essentially. I don't know. Sometimes it, yeah, okay. If I were to take the derivative of f times g, of course, it would be f prime g plus fg prime. F prime g plus fg prime. With a little clever rearrangement, if I integrate both sides, once I have the derivative, if I integrate the right side, and I do it with each term and bring it to the left, I get the integral of f prime g, which is right here, dx, plus the integral of fg prime, right here. And on the left side, which I'm going to throw over to the right, I get the integral of dx fg dx. Now, this looks a little weird, the integral of dx, but Remember that the integral and the derivative are what? Inverses of each other. So they kind of undo each other. So this becomes just f times g. Now, if I subtract from the left side the integral of f prime g, which is that first term, I bring it over here, and I'm left with the integral of f g prime equaling f times g minus the integral of f prime g. Cool. And that's a lot of f's and g's. So for the sake of simplicity, if you just let f equal u, and you let v equal g, you end up with this right here. You get the integral of u dv equals uv minus the integral of v du. Yeah, that's a lot. So if we let u equal w and v equal y, no. This is exactly what we did up above. And the way that I laid it out with the backward z prevents you from having to memorize that u dv thing, right? The integral of u dv equals uv minus the integral of v du. You don't have to remember that. Just remember backward Zoro. Okay? Got it? So that's why it works. Let's do backward Zoro here. We have the integral of 2x e to the 4x. First of all, entertain the idea that it might not be integration by parts. I have e to the 4x, which is the more interesting factor. It has an inside function of 4x. What's the derivative of 4x? 4. Criminy. I'm off by an x, so maybe u sub, right? U sub's not going to work. If you're going to replace 4x with u, it's not going to work. It has to be like 4x plus 1 to be of any benefit. Now, if that had been, instead of just 4x, if that had been 4x squared, we'd have it, right? Because now we'd have an 8x derivative. We'd be off by a 4 if you want to include the 2. You'd have a 1/4 correction, and it'd be e to the 4x squared plus c. But because it's just e to the 4x and u substitution doesn't work, this is a good candidate for integration by parts. Here again is the telltale sign. You have a factor that is a power function, like a power of x. And the other one is going to be something that kind of cycles when you take its derivative, like sine and cosine, right? As you keep taking their derivatives, they cycle back and forth to each other. E to the 4x cycles pretty quickly. It is its own derivative. All right, so that's kind of a giveaway for the most part. I know how to take the derivative of 2x and e to the 4x, and I actually know how to find the integral of 2x and e to the 4x. I have to decide, though, which one I want to take the derivative of and which one I want to integrate. And based upon what I already said, what would you choose? 2x. Now, you do have the option of bringing the 2 out front and letting them just ride around the problem and work with x. Or you could take 2x together. It's up to you. What do you want? I would say bring the 2x along for the ride in this case as one of the factors. So we're going to let u use the one we're taking the derivative of. We're going to let u equal 2x. And then next door here, let dv equal e to the 4x dx. Now underneath there we have du, and below there we're going to have v. So very quickly, before we actually do the work, okay, let's look at the rule. This is your first product that defines the problem, but here's the first one in the answer. It would be u times v minus the integral of v du. And that's what we have up above there. Okay, so with the backward Zoro method, you don't need to remember all those u's and v's and f primes and g primes. It's just it sets up nicely. All right, so what is the derivative of 2x? 2. And what's the antiderivative of e to the 4x? 1/4 e to the 4x. Good. Oh, yeah, 2x dx, that's fine. Yeah. It doesn't really matter. This is kind of most of the time, and I left that off, most of the time I leave the dx off, which is fine, because when you go to your final answer, you're going to go ahead and put those in there. It's up to you. It is proper to put the dx there. It is proper to put the dx there, but this is kind of like the number line chart, where this is not necessarily going to be graded. So if you want to leave those little pieces off, it's not a big deal. Thank you for bringing that up. All right, so here we go. The first product is really the one we want. I'm going to go ahead and make the z, though. So we get a 2x times a 1/4, which is going to be, I'll go ahead and write it out, 2x times 1/4 e to the 4x, and then minus the integral of the horizontal product, which is going to be 2 times 1/4 times e to the 4x, and there's where I would add the dx if I needed to. Yeah, right there, that's what I meant. Right there. There you go. Okay, so there's still some work left to do. This first term, all we have to do is simplify. So that's 1/2 x e to the 4x. It's good. And now over here, minus the 2/4 I can pull out front and call 1/2. But I think, bless you, then I'm ready to integrate e to the 4x, right? One more time. What's the antiderivative of e to the 4x? Another 1/4 correction with another e to the 4x. And then, of course, you put plus c at the end of that. So as long as you still have that second integral there, on that intermediate step, you don't really need the plus c. And then, of course, you can call that 1/8. What would happen if you you misidentified u and v? Have you thought about that already? Would it work the other way? Let us try. If we let u equal e to the 4x, then du is going to be 4 e to the 4x dx, technically. I'll try and establish good habits. dv then would be 2x dx, and v would equal x squared. So here we go. That would define the problem. So the first diagonal would be x squared e to the 4x minus the integral of, if I multiply across, 4x squared e to the 4x dx. We haven't done anything wrong, but we're still faced with that. Ah! This is annoying. Okay, I'm going to highlight it. Watch this. Pretty soon. There you go. Yeah, we're still left with that. Is that something we can anti-differentiate? No, in fact, that's a good candidate for integration by parts. And you would let probably u equal x squared, right? But if you misidentified it, guess what's going to happen? You're going to be building up. The next one is going to have an x cubed. So you're not doing anything wrong, but you keep taking that other integral that you have to evaluate further and further away from where you want to take it. You're trying to reduce the powers to get rid of it. So that's why you want to let that little power function of x be the one you take the derivative of, because it makes the problem smaller. Okay, evaluate x natural log of x. Without integration by parts, do you see why it can't be done? If it were the natural log of x divided by x, we'd be in business, right? What would be the inside function? ln of x, and its derivative is 1 over x. We wouldn't be off by anything. It'd be 1/2 natural log of x squared. But because the x is in the numerator, the derivative of the natural log of x is not x. And the derivative of x certainly isn't ln of x, and we're already stuck. So, notice we have two factors. On the first factor, we know how to take its derivative, and we know how to integrate it, yeah? On the second factor, we know how to take its derivative, and that's it. Do we know how to find the antiderivative of ln of x? We've never learned that. So, if I can't take the antiderivative of the natural log of x, that is, I only know how to take its derivative, that kind of forces my hand, doesn't it? I can't call x u like I would like to, because I would have to find the antiderivative of ln of x, and I don't know it. So this would be the exception to that kind of rule of thumb. Let your power of x be u. It's forced to be the other one. So we have to let u equal the natural log of x, and we have to let dv equal x dx. All right. What would du be? 1 over x dx, and then v would be 1/2 x squared. Now, doing the backward Zoro. I'll do it again. Pick pink. Backward Zoro. There we go. The first diagonal, remember, is the one you want. It equals 1/2 x squared natural log of x minus the integral of the bottom product, which is going to be 1 over x times 1/2 x squared, and I'll put the dx at the back. Even though this 1 over x has the dx there, that dx should go at the back. So half of it is done, or part of it is done, 1/2 x squared natural log of x, but we're still left contending with that integral. And remember, I was forced to choose x to be dv instead of u. As we just saw in the previous example, it kind of tied me up. I couldn't do anything with it. But what happens here? I have an x squared times a 1 over x, which gives me what? Plain old x, right? And I could pull the 1/2 out front, actually, and that leaves me plain old x. Do I know how to find its antiderivative? Heck yeah, even Schroeder's eyes got big as saucers. He knows it can be done. So x becomes 1/2 x squared, right? Times the 1/2 that's already there, 1/4 x squared, and then plus c. So it worked out. We would prefer, again, remember, to let the power of x be u. But sometimes we have to let it be the other one because the other factor we only know how to take the derivative of. And the natural log of x is one of those examples. Okay. Hey, I'm wondering what the antiderivative of plain old natural log of x is. Would that be one worth memorizing? You think it shows up enough? Go ahead and find it on your own. Yeah. I don't know. I'll see. You'll let me know, right? What if I told you, yes, you can run a mile in under 4 minutes. It can be done. You can find the antiderivative of the natural log of x. Does that empower you now to do it? No? DNE. You must be in doubt? Backward Zoro. What'd you call you? Well, yeah. Yeah, perfect. Yeah, I like it. I like it. You got everything identified correctly. That's a critical first step. Again, the backward Zoro method is just a way to help you organize your information, kind of like the table that I gave you for Euler's method. So you don't have to memorize a formula. Just make sure you put your U first. It comes before V in the alphabet song, right? Plus what at the end? Plus C. Good. Most of y'all look like you're getting it. You're identifying the right thing. There's not a lot of options, really, right? The key is to know that you could do it by parts. It is in this section, right? So you're anticipating maybe to do it by parts. So that's kind of a giveaway. You would call U ln of x. And dv, you would call 1 or dx, whatever you want to do it, or 1 dx. It's kind of the implied factor that's there. And, of course, du is 1 over x, and v would be x. The antiderivative of 1 is x. So the backwards Zoro method gives you x ln of x minus the integral of, always minus the integral of, the product, which is 1 over x times x. And notice I left the dx off right after the 1 over x, but I did put it in my integral, so I'll add it back up there. And so what we're left with should be an integral that's manageable, right? 1 over x times x is 1, and the antiderivative of 1 is x. And then, of course, 1, you add what at the end? Plus c. Very good. So if you have room in your hard drive, your mental hard drive, that is, upstairs, this might be one you want to add. But if not, it's pretty easy to derive as needed. Now, having said that, if you now consider that you know the antiderivative of the natural log of x, would you retreat back up to the previous problem and let u equal x and let dv equal this? I don't know. I'll let you try that at home. I don't think I would, because it worked out pretty nicely the other way. But x ln of x minus x plus c. X ln of x minus x. You want to check it, or did you already check it? Does it work? You checked it? Let's see. The derivative with respect to x, by the product rule, we get 1 times the natural log of x plus x times the derivative of the natural log of x, which is 1 over x, minus 1. What is x times 1 over x? 1, and 1 minus 1? 0. So we're left with the natural log of x. It works. Yeah. X ln of x minus x. Okay, so notice that everything we've done so far has worked with this backward Zoro method. It's been one iteration. We've written it out, and we've had one integral, and we've been done. But it doesn't always work that way. And that was the wrong segue. That was the segue for number 8. Yeah. Let's do example 5, and we'll come back to that segue. The integral of arctangent of x. This is kind of like the one I just had y'all do, right? Integral of ln of x. We knew how to take the derivative of ln of x, but not the antiderivative of it. Kind of the same thing with arctangent, right? We know how to take the derivative of arctangent, but not the antiderivative. This seems like a case for what? Integration by parts. Yep. What would you call u? Arctangent of x. Good. Again, you're kind of limited. And dv would be dx, or 1, dx, whatever, or 1. Du then, what's the derivative of arctangent? Good, 1 over 1 plus x squared. And v becomes, and then you should put a dx there, v becomes x, right? So backwards Zoro, you get it equaling x arctangent of x minus the integral of x over 1 plus x squared, essentially, when you multiply across. All right, so it looks like part of it's done. We got x arctangent of x minus. Now that integral is something we have to contend with. What's the inside function on that integral? 1 plus x squared, right? It's inside something to the first power. What's its derivative? 2x. Do we get the x in the top? Yep, we're only off by a 2, which means we have a correction of a 1/2. The x gets packaged back up, and it becomes a what rule of integration? Natural log. Now, the absolute values is part of the natural log rule, but because it's 1 plus x squared, is it okay to leave them off here? Yeah. But is it okay to also keep them on? Yeah. And then, of course, plus c. There it is. So integration by parts. Works well when you know how to take the derivative of something, but not the integral. And so you're finding the antiderivative by taking the derivative. Kind of like in pattern recognition, that was the first thing we did. Pretty cool. Kind of fun. Another strategy, another technique. All right, y'all do this one. Y'all do example 6. I wouldn't necessarily memorize the one for arctangent. All right, y'all do it. Don't look up here. I'm going to do it too. Unless you get stuck. Feels like it. Remember, every time you are faced with an integral, you treat it kind of like a brand new problem. It could be like the third step inside of another problem, but if you redefine an integral, reset your mental flowchart, all the methods are back on the table. Yes. Oh, Jen. Okay. All right, I'll go over it if you found the insight. Keep going. So we got x times arctangent of x, and maybe based upon, again, example 5, you think you know the antiderivative of arctangent, so you want to call it dv. I don't know if you tried that, but it's going to get kind of messy. So again, I would prefer to call x u, but because I have an arctangent and I technically don't have its antiderivative memorized, I'm going to let it equal u. I'm going to force x to be dv. So derivative of u is 1 over 1 plus x squared dx, and the antiderivative dv is 1/2 x squared. The backward Zoro gives you the diagonal product of 1/2 x squared arctangent of x. That piece is done. Always minus the integral of the horizontal product. So I brought the 1/2 up front, and you're left with x squared times 1 over x squared plus 1. I commuted the terms in the bottom. So x squared over x squared plus 1, if you're looking at it, you might get stuck there again, right? Because the derivative of the bottom is 2x, not an x squared. And then at some point you have to remember when you have a quotient, and you can't split it up, right? Because you can't split up denominators. Long division works well when the degrees of the top and bottom are the same, or the top is larger. So I came out here and did long division, which is why I commuted the terms in the bottom. And you can rewrite the problem as the quotient, which is 1, plus the remainder, which is -1, over the original divisor x squared plus 1. Now notice the notation. The 1/2 is still out front with the brackets. So when you integrate, you still have your minus 1/2, parentheses or brackets, x minus, and then it's an arctangent of x. So then I just distributed the -1/2, added the plus c. By the way, you do need to put the plus c as soon as the last integral is gone. You don't really need it on this intermediate step because this second term with the integral still kind of has that unresolved plus c in it. And there you go. There it is. Three different terms. So that one's a little more interesting, kind of a combination of methods. Is this the segue part? Let's announcements. Stupid. How about this one? Let's do this one together. We got theta, inverse secant of theta, d theta.
Announcement. We have an important announcement about Mr. Vega, our beloved counselor. We just want to let you know that February 26th, that's next Friday, Mr. Vega will be leaving New Braunfels High School to pursue a job opportunity out of state. We are sad that he will be leaving us, but we wish him the best of luck in his new endeavors. Students, we want to let you know that we are actively looking for a counselor to replace him, and until we find a suitable candidate, we are going to take care of all the students in his alphabet by having the other counselors see you as needed. So I want to let you know that we will still support you in your course selection and any questions that you may have. We did send an email to all parents in this alpha for Mr. Vega to let them know that we are looking for a new replacement, but in the meantime, all the emails and phone calls we're going to divert to our other counselors, and all your needs will be taken care of. If you have any questions, please feel free to see Mrs. Gonzalez, the counselor secretary, and she can help you.
And teachers, at this time, if you could please turn your TVs to channel 4 for the morning announcements. You can also view them online at mbhstv.com.
The girls are staying behind to finish the school year. Yeah. Okay, so on this one here, narrating through it, it's kind of like the one before. You're letting u equal theta, and then, u equals inverse secant of theta, and dv is equaling theta. And it works out kind of the same way, but the only interesting thing is the derivative of secant, remember, generates that absolute value of theta in the bottom, so there's that extra factor, so that when you, well, this is super way behind. There you go. So that when you multiply across, you have a theta squared in the top, and you have that absolute value of theta in the bottom. So if you get rid of the absolute value of theta, and you make a note maybe that theta has to be greater than 0 off to the side for that one, it'll show up. Then you could divide out one of those thetas, bringing that square root to the top, and now it's going to be a power rule because the derivative of theta squared minus 1 is 2 theta, right? See that? The derivative of theta squared minus 1 is 2 theta. So again, I'm writing down all this other stuff that's already done, the part that's completed. So I have minus 1/2. I'm off by a 2, so I'll have a correction of another 1/2. And then that theta gets packaged back up, and now the rule of integration is blob to the negative 1/2, which is blob to the positive 1/2, times the reciprocal 2, and then plus c. So kind of long and involved there. And then you can simplify. Integration by parts. Practice, practice. There's some good ones on the worksheet for you to practice. Now there's 6 minutes left here, so I do want to talk about the one from the movies, okay? Revisiting Pancho's problem. He was doing x squared sine of x, okay? Now, if you had your choice based upon your experience already, which one would you call u? X squared, because in this case, we know how to find the derivative and the antiderivative of both factors. So we have the flexibility of choosing whichever one we want. And as we've already seen, if I let sine of x equal u and dv equaling x squared, I'm building up the power of x, and there's nothing in the sign that's going to break it back down like there was for the natural logs derivative when it became 1 over x. So here we would force u to be x squared and dv to be sine of x. And what was Pancho doing? He was doing the opposite. He was letting u equal sine of x. So he was doing it right. Notice you can see kind of vaguely there he has a 1/3 x cubed, but he was just building it up further and further away. And in the movie, Mr. Escalante didn't tell him, you have chosen the wrong u and dv. It was a much more powerful scene where he says, do you want me to do it for you? And Pancho said yes. But the correct thing, he was supposed to say no. Because if you have the ganas, if you have the desire, you don't want people to do it for you. Okay, so let's do it for ourselves. Using the correct identification here. U is x squared. So du is 2x dx. And v is negative cosine of x. And so using the backwards Zoro, we get it equals negative x squared cosine of x minus the integral of the product along the bottom, which will be a negative 2, so I can make that a plus 2 outside, an x cosine of x dx. You'll see that? If it shows up. Come on. The product along the bottom is a negative. It's a minus always in front, so minus the integral, times the negative makes it plus, and we bring the 2 out front, but we still have an x cosine of x. So once again, we're faced with that integral. Now looking at that, up to now, this is the segue from earlier, we've been able to compute that by a method in our head. But looking at that, how would y'all need to compute that? I would need to do integration by parts again. So you'd have to do a little nested integration by parts. You'd have to go let u equal x and dv equal cosine of x, and du would equal dx, and v would equal sine, and you'd have to do it all over again, right? And it will work. What? Schroeder? So this method will work, but you're going to have to be careful because now it's going to be plus 2, beefy bracket, and you're going to have to distribute the 2 to everything in there. So this would be a nested problem. Now, what if this problem had been not an x squared, but an x cubed? Guess what you would do? You would use integration by parts. And you'd have the first one, which would take it down to an x squared. And then you'd have x squared cosine of x, and you'd have to do a nested loop to get it down to x. And you'd have to have another nested loop. So whenever you have this function here, this power of x, and it's more than 1, if that's like something that you're going to let equal dv, like sine of x, cosine x, e to the x, and you're going to call x squared u, the power on the x is going to tell you how many iterations of the backward Zoro you're going to have. When it's a 1, no big deal. That's one backward Zoro. You can handle that other integral inside of it. But if it's 2, you're going to have a nested. And if it's a 3, you're going to have 2 nested. So there's a better way to do it. There's a better way to do it when that power is greater than 1. And it's what Mr. Escalante in the movie calls the tic-tac-toe method. Some people just call it the tabular method. So here's the tabular method. You still have to identify u, and you still have to identify dv. But here's what you're going to be doing. You're going to be creating a table. The right column, the rightmost column, is just going to be a plus or minus column. All right, now here's what you do. You assign u to be what? X squared. And then you take its derivative, which is 2x. And what's its derivative? 2. And what's its derivative? 0. So what you do is you kind of expire it all the way down the column. You just keep taking derivatives on different rows. X squared, 2x, 2, 0, and then dv, we're going to call sine of x. And we're going to have to finish this tomorrow. What is wrong with technology today? Gee, shut up, Siri, or whoever your name is. I don't even know if she has a name. Google? Okay, we'll finish tomorrow. Have a great day.